Thank you. All right. So, hello. Thank you for the introduction. My name is David. I work for Heptio. I've worked there for the last year and the next week. And then we're being bought by VMware. So, I'm going to have to change my slides and stuff. So, Heptio are a plucky little startup. We're founded by two of the originators of Kubernetes, Joe and Craig. We build tools, automation, visualization, things on top of Kubernetes to make it easier to use. Just as a quick straw poll, is there anyone in the room using Kubernetes or thinking of using Kubernetes? Excellent, excellent. So for those who aren't, this is actually from the Kubernetes.io website. Kubernetes is an open source system for automating deployment, scaling, and management of containerized applications. So it's clear as mud, right? There's this persistent meme that Kubernetes is complicated. And that may be true, but I think it's more a matter of perspective. Like this little clicker here, it has 4 buttons, has a very simple interface. You might argue that it's simple, but if you went all the way down to the semiconductor physics of how the microcontroller and the radio worked, that's really complicated. So I think it's a matter of perspective. So at the level that I expect most of us in this room would interact with Kubernetes, possibly an application developer role or building tools to integrate with Kubernetes, you can really think of it in 4 layers. The first one, the lowest, is a replicated data store. Kubernetes by default uses etcd. There's not really any way to change that. From the point of view of a developer interacting with Kubernetes, you can effectively ignore this. From the point of view of an operator, if you are managing a Kubernetes cluster for somebody else, unfortunately, you have to treat it like you treat all databases in state, which is like a live hand grenade. The second is the API server, and this is generally what people think about when they think of Kubernetes. The API server sits on top of the data store. We add authentication, schema validation, your basic CRUD operations, as well as watch, which is really the crucial one. So on top of that, we have controllers and operators, and they watch the API server and try and match the world to what they see in the database. So a good model of thinking about this is that the API server behaves sort of like a message bus. You can observe documents arriving and changing and leaving, and you can therefore write code that reacts to that. If you have in your mind the model of the Windows registry, it's pretty close. The last one is a container runtime, which by default is Docker, although there are many, many competitors in this space. And this is fundamentally what is going to run your containerized applications, doing so under the control of all these other layers. So that's really Kubernetes in a nutshell for the purposes of what we're going to talk about today. There are obviously many, many levels that you can dig into, but for the moment, I think this suffices. So the part of Kubernetes that I spend my time on is something called an ingress controller. Ingress controllers are responsible for getting the traffic from the outside world down to the applications, your containers running inside a Kubernetes cluster. In practical terms, ingress controllers provide HTTP, TLS management, load balancing, reverse proxying, all that good stuff. And they provide it as a service to applications running inside the Kubernetes cluster. Just as things like the scheduler provide the ability to replicate workloads, to move them around, to detect when one has failed. Same idea. Now that's a pretty broad remit. So one of the ways that I approach the design space for an ingress controller is to say that there should be a good ingress controller should take care of that 90% use case that traditionally in your web stack you would have to have pulled out Apache or HA proxy or something like that to do some bits of HTTP middleware. here are, I think, probably the 4 key things which ingress controllers add to Kubernetes to give you that as a service type of approach. The first one is traffic consolidation. It seemed that most people were comfortable with Kubernetes. So you may know that you can ask Kubernetes to request, say you're running in Amazon, an ELB, and then to forward that traffic down to your containers. Now, that's great. That means you get one of your applications online behind a public IP. That's great. You do that pattern over and over again for every application you deploy. That's a lot of public IPs. If you're in Amazon, that means you're probably going to hit some rate limit somewhere. That has cost, obviously, and more importantly, has like a maintenance overhead. There's now an extra thing that's involved in delivering that application, an extra thing that can go wrong. More importantly, depending on the security posture of your organization, they may not be totally cool with you having tens or hundreds of public IPs just sloshing traffic into your cluster. They may really want it to go through one central place that they can audit and understand, this is the open port, this is how web requests get into our applications. The second one is TLS management. A while back, Chrome made a change that made non-HTTPS sites marked as insecure. And really, it's nearly 2019. Everyone should be using TLS. We have projects like JetStack Cert Manager and the Let's Encrypt project, which are going to take care of obtaining and renewing that certificate. And an ingress controller can take care of the other half, which is presenting that certificate behind some port 443 to do your S&I negotiation and do all that TLS handshaking. The third property of an ingress controller is that we should be able to talk about describe the structure of our web applications in an abstract way. We all know that you can't just take an Apache config and dump it on Nginx, and you can't do the same either way. A really useful thing of ingress controllers is that you can talk about the different, like your TLS section, your certificates, your HTTP2, your WebSockets, all these properties of your application in an abstract form, in a way that you can move or deploy your application onto different Kubernetes clusters that may be using different ingress controllers without effectively having to rewrite what was an Apache config in one deployment to HA proxy in another. And the last one is path-based routing. If you're using an ELB to bring traffic into your application, then you get that at layer 4. You get TCP. It's your job to stand up a HTTP server and handle it at that level. It's also your job that if your application, you want your static traffic served from one place, you want your /ads to go to a different service, you want the dynamic data from your application to go to a third service, you're responsible for doing that inside your container, inside your application. And so you're kind of back to that previous point about not really having an abstract configuration. You've had to encode it into your application. So ingress controllers also provide you the ability to do this path-based routing effectively as a service provided to you by the Kubernetes cluster. You say, this host, this set of routes, go to that application. So what is Contour? Contour is an ingress controller that exists to fulfill this set of requirements. As with most ingress controllers, our distinguishing feature is that we use Lyft's Envoy proxy for a data plane. We borrow that terminology from the networking folks. So the Nginx ingress controller uses Nginx. The GCP GLB ingress controller uses Google's global load balancer. So ingress controllers generally follow, while they aim to offer these features, they follow the data plane that they've chosen. So why did we choose Envoy? It turns out that Envoy is a really good match for this declarative nature of the Kubernetes API server. Envoy is a proxy designed for dynamic configuration. And the key argument that I'll give you for why I think this is different is all of the appliances, web servers, switches, F5 load balancers that I've worked with in my career, most of them have some kind of CLI or network or admin interface that you can go to ask it to add something or change or remove something. But the key is that that configuration that you're modifying lives on the appliance. It is the source of truth. This has been pretty much the theme for all of the equipment I've worked with over the years. Envoy is different. It actually considers itself to be a client of something else which is going to give it its configuration. By default, Envoy doesn't do anything. It just connects to what it calls the management server and waits to be given configuration. And so it is not the source of truth. It waits for the configuration to be streamed down to it. And this means that it's designed from the ground up to expect a changing configuration almost constantly. And this fits really, really well with the Kubernetes model. If you think about the way that Kubernetes puts containers and pods onto machines, the kubelet running on each of those machines, all it's interested in is to see a record arrive with a host name that it's looking for. It doesn't know how that pod was created, doesn't know whether it's a deployment, a replica set, hand edited. It's not interested in that. All its job is to make what it sees in the API server match what's running in its world. When that record goes away, it's going to turn off the pod, and it is no longer involved with it. And very much so, this is the way that we do things with Contour as well. And what this boils down to is that Contour is just a translator. We take the Kubernetes REST API on one side, and we translate it on the fly into the gRPC form that Envoy needs. And that means as soon as a change is broadcast from the API server, we stream it directly to Envoy. There's no reloading, there's no writing config files to disk and hupping, there's no child processes and kind of a long stream of processes that are hanging around waiting for connections to finish up. All of that is handled directly by Envoy because it's built to do this. And it turns out there's some really good synergies between the Kubernetes data model and the Envoy data model. For example, ingress objects in Kubernetes map directly to listeners and routes. LDS stands for Listener Discovery Service. That's just the name of the gRPC that gRPC gives it. So ingress matches to listeners for what host and port, and routes for the actual route configuration. Services in Kubernetes map almost directly to Envoy's notion of clusters, which are the backends that traffic is sent to. Things like secrets, where we put TLS configuration, that's mixed in with the ingress. Ingress mentions a TLS secret by name. We find those details, we send them to the listener service. And endpoints, which are the list of IP addresses and ports for a particular container running on a host, map exactly to what Envoy needs in what it calls the endpoint service. Cool. So that is a whirlwind introduction to Kubernetes, Ingress, Contour. For the rest of the talk, I want to change things up and I want to talk about Contour, the software engineering project. So when I was a child, one of my favorite lunchtime activities in primary school was when it rained, because when it rained, they would shepherd us into the building under the library and we would watch 16mm films, watch cartoons, watch all sorts of things. And one of the strongest memories that I have from this time was a film that I'd later learn its name was called Powers of 10. Does anyone remember this film? 1977? Yeah, you do. So Powers of 10 was a 9-minute film sponsored by PBS, directed by Charles and Ray Eames. And it started from this human scale notion of two people having a picnic, and it zoomed out in powers of 10 to the edge of the known universe, and then zoomed back in down to the subatomic level. So by way of segue, I want to explore the developer experience of building software that for and inside Kubernetes using Contour as a case study. And we're going to move from the micro to the macro and back again. So like most of the Kubernetes ecosystem, Contour is written in Go. This is certainly not a hard requirement, but given that Kubernetes itself is written in Go, the Kubernetes Go client is written in Go, and the Go is purpose-built for writing these kind of autonomous systems, it's a reasonable fit. It's not the only way you can do it, but it's certainly the path of least resistance when what you actually want to do is write a program rather than re-implement a client library. So of the last release we did a couple of weeks ago, I ran the numbers, and Contour is just under 21,000 lines of code. That's around 5,000 lines of source, and the other 16,000 are tests. And I kind of think that that's the right ratio. Interestingly, the ratio of code to tests has only increased over time. Partially because if you think that Contour's main job is data transformation, we have a lot of, for this input, I expect this output kind of testing. But also, Contour is a moderately complicated component for Kubernetes. I think it's a reasonable level of complexity. And so if you find yourself implementing your own Kubernetes component, so you're writing an operator or a controller, and you find yourself heading into tens or hundreds of thousands of lines of code, that would be a signal to me that you're probably trying to do too much in one place. You're taking on too many responsibilities, and you should try to revisit your design and try and break it down into smaller, independent components. Because I just don't think there's a call for a 100,000 line Kubernetes controller. And on the topic of not doing a lot, a piece of advice I have for you is to keep your main function in your main package as small as possible. And some of the reasons for this is that main packages are traditionally hard to test. They parse command line arguments, they manipulate global variables, they expect files to be on disk, and not just on disk, but in a certain place on disk. And they absolutely never expect to be executed concurrently. So right there, that it makes it very difficult to write a test that executes in parallel with others because of these requirements. So it's a lot of state to track or mock. And this is going to make your test pretty brittle. So instead, the rule of thumb that I have is your main function should maybe parse your incoming flag. So you set up some flag parser and do that work. You read your configuration from disk or environment variables if you go that way. Set up your big connections, like to your database connections, or your Kubernetes, in Contour's case, the Kubernetes API, because without this, your application can't start. So you may as well get that out of the way as soon as possible. Set up your loggers, obviously, and then pass all that information that you've collected down into your business logic, and then the rest, all of main's job is just to wait for your main business object to return, and then you just exit with success or failure. So always keep refactoring your main package to move as much of that business logic out of there as possible. This is going to make your testing easier. It's going to end up avoiding strong coupling to global variables. So let's zoom a little bit further out and look at, this is a slightly edited view of Contour on disk. We have the actual Contour command that we talked about. We actually take the Kubernetes objects and build them into a directed graph, which helps us normalize a lot of the ambiguities in the Kubernetes data structures. So we actually build our own graph of the bits of the Kubernetes API that are important to us, like we map virtual hosts to routes and then backend services. We then pass that to a translator, which effectively is just the visitor pattern. It just walks over this tree of nodes and builds the different data structures that you saw on that previous slide. So we have different visitors for getting data about endpoints versus getting data about listeners. We have our integration tests, which I'll talk about at the end here. We have, it says here, Envoy helpers. The communication between Contour and Envoy is over gRPC, and that involves protobufs. Now, hopefully some of you have had some experience with using protobufs in Go. They're pretty verbose. Like there's a lot of just building data structure inside data structure inside data structure. But by putting them into their own package, with the inputs of those package are from the DAG, we can put all the business logic for transform this that I just walked across into the right Envoy data structure. And we do this completely isolated from any notion of Kubernetes or gRPC. So all of that business logic is in there, and it helps us avoid kind of duplicating these big data transformation tests in other packages. We have some gRPC helpers. This is it implements just the handshaking for what Envoy calls XDS, which is just the name for the message that goes back and forth between Contour and Envoy. And we have a few Kubernetes helpers for doing similar things, setting up watches on the Kubernetes side. And so one piece of advice that I would have for you is, like, when you're naming your packages, try and name them for what they provide to the caller. Don't name them for what's inside them. The rule of thumb that I suggest to people is that the name of your package is a one-word elevator pitch for what it can do for them. So names like util and base and common pretty much fail that bar. It's common in projects, especially that come out of the Kubernetes kind of house of development, to put all your code into a directory called PKG. That's just kind of a meme that has stuck around. I think it's kind of a bit redundant, although I do see the similarities with the CMD directory. But what I want to offer is an alternative suggestion, which is instead to put code that you don't intend for others to use. Because don't forget, in Go, we just have public or private as visibility modifiers. Put it in a directory called internal. You saw on the previous slide, almost all of that code was inside the internal directory. And the reason you do this is that internal is a special name recognized by the Go tool, and it will prevent other code importing it unless it is a direct sibling. So other code in your project can import that code, but somebody else cannot import my repository and use it in their project. And this means that by default, all of that, because people can't import that code, they can't rely on it, which gives you a lot more ability to refactor it. If you're the only consumer of it, then once you make the test pass in your own project, you're pretty safe that you haven't broken other people that were inadvertently relying on those symbols. Now, of course, if you decide that we actually want to make some of this, we actually want to commit to this as a public API, that's the time to move it out of your internal directory and get serious about making it part of your versioned API. But by default, try to keep things internal so that you don't have people inadvertently depending on symbols that you never expected them to. So the next thing I want to talk about is Go routine management. Now, one of the main reasons why I think Go is used for this class of application is because of the lightweight concurrency. And so Contour is one program. It runs as one binary. But inside, there are a bunch of different threads of execution doing different things. For example, the Kubernetes API presents a callback approach. So you have to run a function called watch and provide it a callback to be hit on whenever something that matches that watch filter arrives. And so that means just in Contour, we have to manage, we have to watch ingress, services, endpoints, secrets. There's actually a few more that we watch now. We also need to run the Go routine to host the gRPC server, and also one for the HTTP server that listens on the local host for the pprof debug endpoint. So that's that's half a dozen different Go routines that represent a running Contour process. And why this is important is that the lifetime of these is not independent. They all need to be running for your application to be usable. It's not appropriate for one of the listeners, just say endpoints, to stop working, but the rest of the application keep running. That's a broken state. Also, similarly, I imagine your operations team would be pretty upset if they came along to use the debug service and found that it had stopped working a couple of weeks ago. So we need to have the ability to tie these different Go routines together such that one lifetime affects all of them. What we came up with is something we call a group. It's pretty straightforward. You create a new group and you call add with a function representing each Go routine to be run. So you register them all up front. Then in the main run method, we're going to fire off each of those registered functions in their own Go routine. And when one exits, so when one returns to the result, we're then going to close the stop channel and asking all the rest of them to shut down, and then wait for those to shut down. So let's have a look at how we use this. So at the top, we just make a new group. This is actual code from the main function of Contour, just slightly edited. We pass that group to a helper, which is going to register the watcher for the service, the endpoint, the ingress, so on and so on with the group. So each of those functions is going to be registered. We add one for our debug pprof server, and we add one for our gRPC server. And then when we call run, those functions that have been registered are all going to start in their own Go routines. When one of them exits, all the rest of them will be asked to shut down, and g.run will not return until they've all shut down. So we know at that point that there are no dangling resources, there are no dangling Go routines running. This is super critical if you've ever tried to end-to-end testing, where you need to make sure that all of the components have shut down before you start your next unit test. A while back, we actually put it into its own repository. So if this is something that's interesting to you, this is definitely not a novel idea. There are many different versions of this. This is just more tailored to the shape of the callback functions that the Kubernetes client offers you. It wants a very specific signature for the things that are run in the background. Okay, it's time to talk about dependency management. Dependency management is not one of the highlights of Go's history. It's a pretty sorry story. So I wanted to talk about how we do our dependency management on Contour. Okay. So at the moment, we use dep to do our dependency management. Now, the Kubernetes client has been traditionally quite hard to use with tools like dep and glide. It's been hard to use with all of them. Fortunately, this has improved a lot. Release 6 was pretty good. That was in terms of the dependencies and the way it expressed its dependencies was much easier for management tools to work with. Going from release 6 to release 7 was virtually painless. It was just changing, from v6 to v7 up there. And going from 7 to 8 was similarly painless. So this is, after a lot of trial and error, the 3 magic lines that you need if you want to build a Go project using dep that depends on the Kubernetes client. This is pretty much the magic sauce you need. The second thing we do on Contour, which might be a little bit controversial, is that we don't commit our vendor directory to our repository. This is for several reasons. The first is that it just keeps our repository smaller. Those 21,000 lines of code that I spoke about don't include the near million lines of dependencies that the Kubernetes client brings in. Why you need 1 million lines for a Kubernetes client is not really in the scope of this debate. I don't understand why. But by not committing this, we just keep the code that we wrote in our repository. And so instead, to fetch the project, you'd go get the source as usual, go into the directory and just run this one extra command, dep ensure vendor only. And that says, play back the contents of go-package.lock. If you're coming from an NPM or a Ruby world, you'd be like, well, this is just how we do it in the rest of the world. Unfortunately, it took Go 9 years to catch up to this. This does have a few drawbacks. The first one, obviously, if you change branches, you may need to rerun dep ensure. In practice, this doesn't tend to be a problem because our dependency set is very stable. We have a small set of well-known dependencies, and they usually only change at the start of the development cycle. I'll usually put a card in the backlog to say, freshen our dependencies. If there's a new, so for example, there's a new release of Kubernetes, we do that upgrade very early in the cycle, and then that's done. And then, we have 6-8 weeks without any more change of that. And also, if you do get some kind of weirdness or a compilation failure, then you just need to rerun dep ensure, and you're back and good again. The second one, and where I say controversially, is that this obviously doesn't protect us if a dependency goes away. There's a reason why the vendor directory was added to the Go project, to give people the ability to check in copies of their dependencies. Now, as someone who wrote a dependency management tool for Go, I should probably talk a little bit about why, try to justify my position. The first is that as an open source project, the dependencies that we rely on are mirrored in millions of other Git repos already. There are tens of thousands of copies of these in every other Kubernetes project out there. So if the upstream did go away for some reason, finding another copy of it with the exact matching hash would not be difficult. And the second is that given how many people rely on this dependency set, the Kubernetes client is relied on by Kubernetes itself. So given how many people rely on this, the chance of if something did happen, it's going to be fixed very quickly by people who are well motivated to make sure get this back up and running. And the last one is that the delivery of this software project is not source code. It's a Docker image. What we deliver to our users is a Docker image in our GCR repo, not the source code. That's not to say we're not open source, it's just the final delivery is that we will do a build on our Jenkins, which will push the image to GCR. So if there is a small problem with GitHub, we can't release that day, that's not the end of the world. I don't think this advice is applicable to everybody. Like, nobody wants to be the one who says, I can't push to production because GitHub is down. But I think for Contour's role as an open source tool building on a stable set of dependencies, this is a pretty good trade-off. It means you don't carry another million lines of code which are just going to clog up PRs every time someone changes them. And what about Go modules? Go modules are landed in 1.11. They are definitely the future of dependency management for Go. What I've talked about is very much an interim step. But there are a few problems, believe me, I've tried. There are a few problems that make Go modules difficult to use. The first one is that they have very strict format for how you lay out packages inside your repository. Not my repository, but the dependencies. So it imposes requirements on how dependencies lay out their source code. And this is trying to impose that structure on an existing ecosystem, which is proven to be tricky. So until the Go team relax their requirements, or they somehow manage to convince the Kubernetes developers to rewrite their entire repository, that represents a blocker to using the module supporting Go. And the second one, and perhaps more pressing one, is that Go modules change the on-disk layout of a Go package. So when it's downloaded, it's actually put into a different place. And that upsets IDEs and other tools that look at the source and do analysis. So I definitely believe that Go modules are the future. It's just probably 6 to 12 months away. I think another release at least before the rest of the ecosystem is caught up. So stepping out a little bit further, like zooming out a little bit further. Because we're developing an application that runs inside Kubernetes. It means that we're fundamentally building our application as a Docker image. So I want to spend some time about how I talk about integrating Docker into the development workflow for this project. First, and probably the smallest, although not in terms of impact, is .docker ignore. Who recognizes this file? Who has that in their repo? Only a few people. All right. Everyone needs to learn about this. When you run Docker build, it will send the entire contents of your working directory and everything below it to the Docker daemon, just in case, because it needs that to run the build step. So this includes the vendor directory, which is in our local working copy, which we don't use and don't need. This includes your Git subfolder with all those hundreds of megabytes of blobs in there, and so on. And so in our case, this was a couple of hundred megabytes. Now, I mean, it's not the end of the world. It's just 100 megabytes over the local socket. But with this one change, we reduced the amount of data and the latency of starting that build to barely a megabyte. I want to give you a little walkthrough of our Docker file and how we actually do that build. So this is the standard preamble, use Go 1.10. At the moment, Go 1.11 produces larger binaries, which you'll see why in a second. That isn't great. Then the next thing we do is we actually install dep inside the image. And then we copy in our Go package toml and lock, and we run dep ensure vendor only. So we're checking out the dependencies that we need inside the Docker build, inside the image. We're not using the working copies on disk. And there's a trick here that this potentially lengthy step is dependent on the previous one. So if the hash of copy go package toml and go package lock has not changed, then it's going to skip this step as well. So what that means is, over time, you very quickly end up with a set of intermediary Docker images, which represent checking out the dependencies that match these files. So even moving between branches, this step is mostly cached, and that helps a great deal because this is quite a lot to download. Then we do the usual copy the source into the Docker image and run go build. And the last one, we're using something called multi-stage builds. Does anyone know about multi-stage builds? Few people. Multi-stage builds are fantastic because this line here from Alpine 3.8, as is just gives it a name, otherwise it'd just be a number. It says, forget everything that's happened before, ignore the intermediary chains and those hundreds of megabytes of intermediary stacked images, and start again. We're going to start again from Alpine. We're going to add the certificates, and then from build, which is from the previous one, just copy the one binary that we need. So that means the final image is just Alpine plus certificates and our binary. It's not hundreds of megabytes of files added and deleted in various intermediary stages. So this is what it looks like when you actually run it, obviously. And you can see here, step 5 is skipped because the contents of toml and lock didn't change the intermediary hash. So that ends up saving a lot of time. And of course, then it just does the build as normal. Building inside Docker, I don't know, I find is significantly slower than building natively. There are a number of ways you can at least cache some of this intermediarily, but it's very fragile. Like, it's based on the contents of the source, so you're not really going to get much saving. And that's really, I mean, this takes a few seconds to run, and the reason why I'm not really interested in optimizing it is because of this step. For overseas friends, I do apologize. This is how long it takes to push a 30 meg image up to the Docker registry from Australia. So I'll save you it in real time, but effectively the time to build, push, and then go to my GKE Kubernetes running in Sydney, kill the pods and have it pull the image down, that's around about 5 minutes. And so my advice is, don't do this. Try to avoid this Docker build and push dance in your development inner loop, because if it is in your inner loop, then you are optimizing for a maximum of maybe 11 attempts in this an hour. You don't want that in your inner loop. What you want in your inner loop is something like this, which is, this is our normal edit test compile cycle. Because we're using Go 1.10, it has automatic build and test caching. So tests are not run if they refer to source code that hasn't changed since the last time. And so effectively, this is what our inner loop looks like. And this is what I want you to kind of stay hungry for. Like if you move into this world of cloud native development, don't be like, oh, it just takes 10 minutes to do a build. I go and have a coffee every time. Try to avoid the trap of doing sequential debugging in Docker images deployed to Kubernetes. So here are some of the ways that we do this. So that was the unit test you just saw. But how do we know if this thing is actually working? Like, there's a difference between test pass and working software. And we have a bunch of ways of doing this to try and avoid that Docker build and push and reload cycle. So in this example, we have Contour running on this laptop. It's using my Kubernetes credentials, so it's talking to my cluster running in Sydney. And in the bottom pane, we have a tool called Contour CLI, which acts as a client in the same way that Envoy does. It asks the same questions, and we get the same responses that Contour would send to Envoy. So we're able to run and check the results that we expect without ever having to push to Kubernetes. Now, the reason this is quite handy is that these are all protobuf messages, and while they're strongly typed, so you know if it compiles, you've spelt it correctly. But if it still doesn't protect you from, well, I expected in this situation that this particular flag would be turned on. This gives me a very, very cheap way of checking, was it actually turned on? I can go and just grep through the output and say, that's the message I expected to be sent to Envoy. It actually turns out that this CLI tool is really useful for operators. So we actually bundle it in the Docker image. It's actually just another subcommand of Contour, so that people, when they have it deployed, can run this they just Docker exec into their container, and they can run this to see the output that's being sent to Envoy. So you've seen how we optimize for our developer inner loop, how we do a little bit of integration testing. And I want to step out again just a little bit further and talk about how we do our functional tests in Contour. In my experience, functional tests are terrible. I find all the projects that we've tried to write functional testing, they are slow. They are the slowest tests. And that almost universally leads to effort expended to make them run in parallel. People are like, these tests are so slow, what can we do to either reuse the MongoDB that was spun up from the last one and kind of clean it somehow, or just try and make them run in parallel? And what that generally tends to do is just make them unstable. And in my experience, this is what makes end-to-end tests a real boat anchor on your velocity. Like the projects that I've been on, where people will happily obsess about their unit tests, but the end-to-end test that only runs in Jenkins because it's the only one that has the ability to do complicated end-to-end test things, people are like, maybe I'll just rerun it. And so the slowest, longest running, most unstable tests become blockers to delivering your software. So like any engineer on a team of one for the most part of this year, I put them off as long as I could. But there are scenarios that unit tests can't cover because there's a moderate impedance mismatch between Kubernetes and Envoy. What we need is the ability to model not just a single interaction. I saw this object from Kubernetes, I expect this fragment, but a set of actions, because as you saw on the table earlier, some operations depend on others. We can't open an SSL, we can't open a TLS host without the certificate material. So we need two objects to be present before we can do the configuration. So there's a sequence of events that happen. This happened, then this happened, then this happened, then I expect this output. So before we talk about the solution that we arrived at, I want to make sure that I'm also talking about the things that we are not testing. Most importantly, we are not testing Kubernetes. We assume it works. And the crucial thing there is that we are not going to spin up a mock Kubernetes or even a kind of faked out Kubernetes API server just to send just so that Contour can see a message. And similarly, we're not testing Envoy for the same reasons. We assume that somebody else has already done this and they're confident that it works. So if we go back to the architecture diagram and we take out the things that we're not testing, we end up with this. We need a way to send inputs to Contour and a way to look at the output that would be sent to Envoy. And you can do this with the standard Go test. You just write it yourself a setup function. In this case, we make a new translator. We create a new gRPC server to serve that translator. We just bind it to a loopback address. Then we dial the address that we just host, so they're now connected together. And then we return to the caller a resource handler or a translator which represents the input. This is the callback that the Kubernetes client will call. We have a client which is the output that we can test the response sent to Envoy, and a shutdown function. And so, again, the input, the output, and then we can just construct Kubernetes objects, send them to the resource handler as if the callback fired from the client, and then test the result was what we expected. And we can just do this pattern over and over again. We can add, update, remove in any order that we want. Again, just checking the results each time. So let's talk about the good and bad points of this. The bad points is that it is very verbose. You saw that yourself. Even with a lot of helpers, there's a lot of code. Those 16,000 lines didn't write themselves. But at least it's explicit. After this event from the API, I expect this state. You will not find in our end-to-end tests timeouts or retry loops or any of that nonsense because we never find ourselves in that situation of, oh, I added it to the API server, I guess it just hasn't filtered through yet. And this means that our end-to-end tests are a lot less flaky, and when they are flaky, we treat them as real failures. We don't say, oh, the test machine was a bit loaded, I guess I just need to make the timeout a bit longer. The highlights. The things that make me think that this approach has some value is that we have a very, very high success rate of bugs reported in the field being turned into test cases like this. I get bug reports on Slack, in GitHub. I can turn, literally, this is the document that I tried to use. I can turn that into a test case, and I can then turn that into a failing end-to-end test case. And we can drill down into the different modules, writing failing test cases as we go, like trying to find the smoking gun. If you write a test case and it passes, the problem wasn't there. It was probably somewhere else. So this lets us write a bunch of failing scenarios. When we actually fix the problem, we now have a bunch of tests to make sure that we don't regress. The other thing is that it's turned out to be a really easy way for contributors to add tests. You always, when someone adds a feature, you say, please write a test for that. This is a very easy copy and paste way for people to do that. They don't have to, because there are effectively proformas for each of the different types of objects that Envoy needs, there's plenty of stuff to copy and paste. And this helps them add the level of testing that you would expect when someone rolls up with a feature to your project. And finally, it certainly doesn't eliminate completely, but it does avoid this Docker push and delete style of debugging, which gets you into, from experience, once you get down into that level, you are looking at a day's worth of work. You're just moving things incrementally, just feeling your way with a 5-minute latency. So thank you so much for your time. This is all I have time for. if you'd like to talk about any of these things, about Go, Kubernetes, please come and find me during the break, I think. Thank you so much for your time.